Hi everyone, the purpose of this video is to discuss the Topic 6 Homework 3, Kinetics Experimental Techniques, and to go through the IB practice problem that we worked on in class. All right, so we saw various methods for measuring the rate of a reaction experimentally. Remember that in general, in order to measure the rate, you're either measuring the decrease in the concentration of reactants over time, or what's the other option? The increase in the concentration of products over time. So either of these are ways to measure the rate of a reaction, and it's just going to depend on the type of reaction, which one is more appropriate, and which experimental technique makes the most sense. So measuring gas production. This is a technique you can use for any reactions that produce a gas. And of course, in this case, you're measuring the increase in the concentration of products over time. So we saw three ways to do that. This one was with a syringe. You should describe the setup really carefully based on what we did in class. If you're not sure, you should, of course, use the slides that you find in the running agenda. One maybe important note here is you must have a tight seal between the tubing and the syringe. And what does a graph look like here? Time in seconds versus volume of whatever gas you're making produced, and that would be measured in cubic centimeters or milliliters. We also looked at mass loss. This only works for heavier gases, so not hydrogen. Hydrogen is too light to register enough of a mass loss to get good data, and same graph time and volume of gas loss, and of course the title is volume of gas produced versus time. This, of course, the unit is, instead of centimeters cubed, the unit would be grams. So for the syringe, and also for water displacement, which we'll talk about in a second, the unit is centimeters cubed. For mass loss, of course, mass is measured in grams. All right, so I've already hinted water displacement. That's where you have a tube filled with water. You invert a graduated cylinder, also filled with water. You have your reaction happening in an Erlenmeyer flask. You attach tubing from your Erlenmeyer flask into the water and then into, oops, let me make sure I'm trying this well, into the water, into the tube. And so the thing that happens is you're forming water here, and it's going to displace the water that was filled in the tube. Of course, your reaction is happening in here. And there's a video of this in the slides. This you also need to make sure that the Erlenmeyer is sealed so that you don't get any gas escaping. And same situation with the syringe and water displacement for the graph that you could make. All right, we also saw change in H plus concentration. In this case, you're measuring the decrease in reactants over time. You add something, that's vague, but in our case, we added calcium carbonate. You could add lots of different things to an acid. We'll learn about this more, of course, in the acid-base unit. And you measure the decrease in H plus concentration. Why would you have had a high H plus concentration in an acid? Well, because that's what makes something an acid. Something that's acidic has a high proton concentration or high H plus concentration. Some notes that we had here, you need to handle the pH meter carefully. Make sure it's calibrated. Make sure to use the storage solution. They're a little bit delicate. This again, time in seconds. Y-axis would be either H plus concentration or pH, and pH or H plus concentration versus time would be your graph. For all of these methods, you're taking measurements over time intervals. So you're measuring the gas produced in the syringe at every 5 seconds, for example, or measuring the mass loss at time intervals. Water displacement, pH. So you're taking these measurements over various time intervals to produce a rate graph. This last measurement, this is a little bit different. Remember, precipitate is a solid product. This again, you're measuring the decrease in reactants over time. And you get the time for an X to disappear. Hopefully you remember that setup, that you have an Erlenmeyer, and then below it you have a paper with an X, and you look, here's someone's eyes, you look from above and wait for the paper to disappear or the X to disappear. And of course, it's going to disappear because you're forming a precipitate. You only produce one data point. You just have that time it takes for the X to disappear. So you could, instead of this, use a colorimeter to get data over time. Just going to write varies depending on what you do. If you use a colorimeter to get data over time, you would have intensity of color in Y over time. You can also do something like we see in the first example down below, where your conditions are something like different concentrations or different temperatures, and you get the time for the X to disappear at different conditions. But the problem with this one is you're only getting one data point, so you can't use it to measure the rate of a single reaction like you can for the other ones. All right, let's see an example of what that looks like. IB practice. I gave you some information that you're going to need in order to solve, so we'll take a look at that in a moment. And let's jump into it. Sodium thiosulfate reacts with dilute hydrochloric acid to form a precipitate of sulfur at room temperature. So I see sodium thiosulfate, hydrochloric acid forming sulfur and also forming some other things. Identify the formula and state the symbol of X. Well, let me see when I form my products what I've used and what I haven't used. So sodium chloride formed NaCl. Okay. SO2, I got, S and S, SO2, so I've used all the S. I've used two O's, so I have an O left and two H's left. What do two H's and an O make? They make H2O. And I notice that everything is balanced. I don't need a coefficient with the H2O. There's just one H2O. State the symbol. Well, it's at room temperature, so what's the state symbol going to be? Liquid. L for liquid. All right. Suggest why the experiment should be carried out in a fume hood or well-ventilated laboratory. Well, they said this in the video we watched in class. We can also see it in this picture here. I see that SO2 is produced from power plants. So what does that tell me? It's probably not good for me to be inhaling. It looks like this is some sort of toxic that's produced from power plants, and indeed it is. So that's the problematic piece there. The IB accepted several different things to earn that mark. And one is that SO2 causes breathing problems. And the nice lady doing the experiment in the video we watched told us that. It's what's called an irritant. It causes breathing problems. They also accepted that it's acidic, which you're able to see here in this picture. They also accepted just that SO2 is harmful. And you do need to identify SO2 in order to get that mark. SO2 has pungent smell. So all of these were accepted by the IB. What was not accepted was SO2 causes acid rain. Causes acid rain. It does cause acid rain, but that was not a sufficient reason for carrying it out in a fume hood. So it causes breathing problems. That makes sense to me. It's coming out of a power plant. It's acidic. It's harmful. Any of those would get you the mark as long as you identify that SO2 is the problem. All right. The precipitate of sulfur makes a mixture cloudy, so a mark underneath the reaction mixture becomes invisible with time. That's that last rate method we learned. So hydrochloric acid was added to sodium thiosulfate at a temperature. Students measured the time for the mark to no longer be visible. So notice their X variable or their independent variable was concentration. They used different concentrations of sodium thiosulfate. And then they took that measurement for the X to disappear. They got just one measurement per trial. So they were not measuring the rate of one entire reaction. They were not taking the rate at this reaction. They just got one data point, one time for the mark to disappear, the time the reaction takes. But the way that they're going to produce a graph here is that they did that for different concentrations for sodium thiosulfate. This is a little bit more complicated. In order to measure the rate, you actually take the reciprocal of time to measure the rate of the reaction. And they're going to walk us through that. All right, so step one was just show that hydrochloric acid added to the flask was in excess. This is just pretty simple stoichiometry at this point. So I'm looking at experiment one. And let me make that look a little nicer. Oops, sorry. There we go. Okay. So I'm just going to do, I just need to show that hydrochloric acid was in excess. So that's basically showing that sodium thiosulfate is limiting. So I'm going to set up the stoichiometry for sodium thiosulfate and HCl. I'm asking myself, if all of this reacts, what is the theoretical yield? And I'm using that reaction from before. So sodium thiosulfate, 50 cubic centimeters times 1,000 cubic centimeters, 1 decimeter cubed times 1 decimeter cubed, and the concentration, moles, Na2S2O3, sodium thiosulfate. I now need to find the theoretical yield for any product. I'm going to choose the sulfur product. You could choose any product. And let me get my coefficient. So sulfur is a coefficient of 1. Sodium thiosulfate also is a coefficient of 1. So 1 mole Na2S2O3 and 1 mole S. And so that is equal to, give me one moment here to do this math, 50 times 0.15 divided by 1,000 equals 7.5 times 10 to the negative 3 moles of S. So if all of Na2S2O3 reacts, this is how many moles of S I'll produce. I'm going to do the same thing for HCl. 10 cubic centimeters, 1,000 cubic centimeters, 1 decimeter cubed, 1 decimeter cubed, 2 moles. I'm using the concentration they gave me. You should write 2.00. I was being a little lazy there. And let me check my coefficients. So 2 for HCl, 2 moles HCl. I need to use the same product as before. So if all of my HCl can react, the amount of sulfur I'll produce, let me do this math. We have 10 times 2 is 20, divided by 1,000 times 2 is 2,000. Probably did not really need my calculator. 0.01 moles S. And so I've clearly shown that HCl is in excess because I've shown Na2S2O3 is limiting. So we have to do this math, and then in order to earn the point, in order to earn that second mark, this was a 2-mark question, in order to earn the second mark, we have to make sure we explain how we know that we showed what they were asking for. So you might do something like 0.01 moles of S is greater than 7.5 times 10 to the negative 3 moles of S. And so I've shown the amount of product that I could make with HCl is greater than the amount of product I could make with sodium thiosulfate, which means that HCl was in excess. Just like they said, HCl was in excess. All right, draw the best fit line of 1 over T against concentration on the axes provided. Well, all I'm doing is I'm plotting the points. So I have the concentration here, and I'm pulling those concentrations from right here. And then 1 over T, they actually took the reciprocal for me. So pretty straightforward to plot. Notice, though, that the concentrations go in descending order. So you need to start your plot down here, 0.030 and 9. So I'm going to do 0.030 and 9, and then I have 0.060 and 16.7, 0.06 and 16.7, right along here, 0.09, 27.8, 0.09 and 27.8 should be somewhere in there. And let's see, I'm going to pull it up here. 0.12 and 37. 0.12 and 37. I think I got that at 37. And then 0.15 and 43.5. 43.5, somewhere in there. All right. So you need to plot the points and then draw a best fit line. You do need to use a ruler to draw the best fit line. So I'm finding a line where it feels like most of the points fit. And so if I were to go way down here, for example, I'm not intersecting with really any of the points. Up here, I'm not intersecting with any of the points. So right here, I'm right in the middle of those points. You do need to use a ruler in order to get that mark. If you do not use a ruler, you don't get the mark. So make sure that you do that correctly. You also should go through the origin, and mine was a little bit off, so let me try that again. Okay. So I think that's about as close as I'm going to get, but you need to go through the origin in order to get a mark, and you need to use a ruler. All right, a student decided to carry out another experiment using 0.75 molar solution of sodium thiosulfate under the same conditions, determine the time it would take for the mark to no longer be visible. So I'm just going to use my graph, and I'm going to find 0.075, so 0.06, 0.07, 0.075 would be right here. Okay, whoops. So I'm just going to make a straight line, and then a straight line to the y-axis And so the time, we have this, that's 22.5. So the time, remember this was the reciprocal, the time is equal to 1 over 22.5 times 10 to the negative 3. Notice the units. And so that equals 44.4 seconds. 44.4 seconds. Just so you know, they accepted anything between 42.4 and 46.4 seconds. That was the range that was accepted here. Okay. F, this is Maxwell-Boltzmann. This is exactly what we practiced in class. So now you have another temperature, and the second temperature is higher. So I'm going to start with a normal Maxwell-Boltzmann that looks something like that. Usually it has a nicer peak than that. Okay, kind of hard to draw sometimes, but something like that. And then higher temperature, what we saw in class was that the peak moves right and also gets more shallow. So it should look something like that. Not the prettiest, but something like that. In order to get the point, you needed to, the T2 peak needed to be lower, and the T2 peak, oops, that's not how you write an E, to the right of T1. All right, explain how a higher temperature causes the rate of reaction to increase. Well, we can do that right with our Maxwell-Boltzmann. And remembering what we talked about with EA, so you could say greater proportion of molecules have energy above energy of activation. You could say greater area under the curve. That's the same thing as saying more molecules, greater area under the curve. To the right of EA for T2. You could also just say, based on the video we watched, the dating analogy video, more collisions between molecules. So any of those would have earned you that mark. All right, I hope this helps. Let me know what questions you have, as always. And I think that's everything. Have a good day.